Okay, for our fourth lesson, we'll be talking about some of the most important concepts in all of math and all of science, in fact. We'll be talking about the slope, average rate of change, difference quotient, and then velocity and acceleration, terms that are very important in science. All right, so let's say that we have this straight line, as straight as I can draw it, and it goes through the points 1, 3, and it goes through the point 5, 10. All right, so the slope of a line is just a measure of its steepness, how steep the line is. And we're going to define slope to be the change in the y value, or the vertical value, divided by the change in the horizontal value, or the x. So we can measure the steepness of this line by the quotient of the change in y over the change in x. So this little triangle is a Greek delta symbol, and we often use it to stand for change. So this says change in y over the change in x. Okay, so we'll define slope to be the change in y over the change in x. Okay. To get the change in y, we'll subtract this y value from this y value. So we can say 10 minus 3, or y2 minus y1. And then to get the change in x, we would want to subtract the two x values. That'll tell us this distance. That's x2 minus x1. So again, to find the change in y, we subtract the y values. To find the change in x, we would subtract the x values. So in this example, change in y would be 10 minus 3 over, and then the change in x would be 5 minus 1. And we would get 7 over 4. Okay. Notice it would not have mattered which one we call point 1 and which one we call point 2. So for instance, we could have did 3 minus 10. That would have given us negative 7 on the top. But if we did that, we would have to do 1 minus 5, and we would get negative 4 on the bottom. So you'd have negative 7 over negative 4, and it would still be positive 7 over 4. So it doesn't matter which one you call point 1, which one you call point 2. Here, for point 1, point 2, point 1, point 2, as long as you do it in the same order. All right, so notice this is a positive number. Notice, as we talked about yesterday, this line is going uphill from left to right, so this function would be increasing. So an increasing function would have a positive slope. Okay, let's look at a second example. All right, so here's another example of a line. It goes to the points negative 2, 7, and 3, negative 1. We want to find the slope, or a measure of the steepness of this line. First thing to notice is that this function is decreasing. So we expect the slope to be negative. So when we get an answer, let's make sure that it is negative. So slope is defined to be the change in y over the change in x. To find the change in y, we will do y2 minus y1 over x2 minus x1. Okay, so let's pick one point to be point number 1, one point to be point number 2, and again, it doesn't matter which one. So let's call this point 2 and this point 1. All right, so if we do point 2, point 1, we will have y2 is 7 minus negative 1 And you have to be really careful right here. A lot of times we'll get careless and we'll just say 7 minus 1. But it's got to be 7 minus negative 1. Okay. And x2 would be negative 2 minus 3. 7 minus negative 1 is 7 plus 1, so that would be 8. Negative 2 minus 3 is negative 5. And it doesn't matter if we put the negative on the bottom, on the top, or out front, it all means the same thing. So this would be negative 8 over 5. And sure enough, the slope is negative, as it should be, because this is a decreasing function. Okay, so let's talk about velocity. Velocity is defined to be the change in position over the change in time. How far you go divided by how long it took you to go that far. All right, so let's look at this example. Suppose we're out and we see somebody driving down the road. We're watching them drive down the road. We've got a table of data here. So 1 hour past noon, this person we were watching driving down the road was 20 miles past a certain town. 3 hours past noon, this person was 160 miles past town. Let's pretend that they were driving at a constant velocity. So constant velocity means that they were going the same speed the whole time, and they were going the same direction the whole time. So they were on this really straight highway, going the same speed the whole time. We want to figure out what the velocity of this person is, the constant velocity of this person. So to do that, we're going to find the change in position. So to find the change in position, we would subtract the 2 positions. So we will say position number 2 minus position number 1. To find the change in time, we'll subtract the 2 time values. So we will do T2 minus T1. So position number 2 was 160. Position number 1 was 20. Time 2 was 3, and time 1 was 1. Very, very importantly, when you're dealing with a real-world problem, you need to keep the units in there. The units are extremely important. So on the top, 160 minus 20, 160 what units? It's not just a number, it's 160 something. So we look over here, and it says miles. So this is 160 minus 20 miles. Okay. On the bottom, 3 minus 1, 1 what? Well, it's 1 hour. So the units are extremely, extremely important. 160 minus 20, that would be 140 over 2. And you see here we have miles per hour. So simplifying that fraction, we get 70 miles per hour. So this person was driving down the highway at a constant velocity of 70 miles per hour. Okay, let's talk about acceleration. So acceleration is different from velocity. Sometimes people use those words interchangeably, but they're different. Okay, acceleration is defined to be the change in velocity over the change in time. So it's a measurement of how fast your velocity changes. Okay, so let's think about this problem. So pretend we got a spaceship maybe flying away from Earth. Okay, the person driving the spaceship ignites the engines. They light the engines. So 2 seconds after they ignite the engines, they're going 440 miles an hour. 5 seconds after they light the engines, they're going 800 miles an hour. So obviously their velocity is changing. They appear to be getting faster. Okay, let's say that they have a constant acceleration. Okay, so their acceleration will always be the same. Their acceleration won't change. Let's make a graph of this. So we're going to put seconds on the horizontal axis, velocity on the vertical axis. So at 2 seconds, I'm going 440 miles per hour. At 5 seconds, I'm going 800 miles per hour. Okay. If the acceleration is constant, then that means for every increment of time, our velocity will increase by the same amount. So if we go 1 second, our velocity will go up by the same amount as the next second that it goes up. So that'll create a straight line. We want to figure out what the acceleration is of this spaceship. So acceleration, in this case, will be the change in velocity. So to find the change in velocity, we will subtract the velocities. So we're going to do velocity number 2 minus velocity number 1 over the change in time. So we will subtract the times. So T2 minus T1. Velocity number 2 was 800. Velocity number 1 was 440. Again, we got to keep the units in here. Very important to have our units. So the velocity is in miles per hour. Time number 2 was 5. Time number 1 was 2. And this is measured in seconds. Okay, so we simplify that. 800 minus 440 would be 360 miles per hour. Over 3 seconds. Simplifying that, 360 divided by 3 is 120. Keep our units in there. Miles per hour per second. Okay, so the acceleration is 120 miles per hour per second. Okay, so that means the velocity is changing at 120 miles per hour every second. Okay, so here's a graph of the function x squared. We want to talk about the slope of this curve. How do you find the slope of that? We know how to find the slopes of straight lines. This is not a straight line. Slope measures the steepness of the line. But what about the steepness of this curve? Well, it seems to change. I mean, the curve is far steeper here than it is here. If you were a little bug walking along this, it would be easy down here to climb up it because it's fairly flat. But the farther you go, it gets steeper and steeper and steeper. Here it's increasing, so the slope would be positive. Over here, it's decreasing, so the slope would be negative. So the slope changes. So how are we going to measure slope of this curve if it's different at different points? Okay, so to do that, we're going to use something called average rate of change. We're going to estimate the slope of the curve at over different intervals. So for example, we're going to find an average measurement of the slope of the curve over this interval, okay, from 3 to 5. To do that, we're going to draw what's called a secant line through those 2 points. Okay, so this is called a secant line. The secant line is just a line that goes through these 2 points, the one at 3 and the one at 5. Okay. Let's find some other values here. So if this is 3, if my x value is 3, then this would be 9. Why is that 9? Because this function is x squared. If I plug 3 in x, I get 9. If this is 5, this would be 25. Plug 5 into my function. 5 squared is 25. Okay. So now the average rate of change will just be the slope of that secant line. We know how to find the slope of lines. So the average rate of change of f from x equals 3 to x equals 5 is, okay, so the average rate of change from x equals 3 to x equals 5 is just the slope of the blue secant line. So that will be 25 minus 9 over 5 minus 3. So this point is 3, 9. This point is 5, 25. So 25 minus 9 over 5 minus 3. 25 minus 9 is 16. 5 minus 3 is 2. So the average rate of change over that interval from 3 to 5 is 8. Now let's think about that. Is the slope of this black curve, is it always 8? No, it changes. So here, is the curve x squared steeper or less steep than the secant line? So here you've got the secant line, here's the curve. You can see that the curve, the black curve, is steeper than the blue line here. Down here, the blue line, the secant line, is steeper than the black curve. Somewhere in the middle here, the black curve should have the exact same steepness as the blue secant line. All right, let's look at another example here. So the same function again, we're going to use x squared. We want to find the average rate of change over the interval from -7 to -5. So here's x equals -7. Here's x equals -5. So if I plug -5 into that function, I'll get 25. If I plug -7 into the function, I get 49. Okay, so we're going to draw the secant line through these 2 points. And I'm going to actually label the points here. So this is -5, 25. This is -7, 49. So I want to find the average rate of change of that function over that interval. So that would just be the slope of secant line through those 2 points, -7, 49, and -5, 25. So we've got y2 minus y1, that'll be 49 minus 25, and -7 minus, and be really careful, -5. 49 minus 25 is something, 24. That is right, I think. And -7 plus 5 is -2. So we get -12. We got a negative slope, and it should be a negative slope. The function is decreasing at that point or over that interval. Okay, let's try an example with a different function. This time we'll use the square root of x. We want to find the average rate of change over the interval from 9 to 16. Okay, so we will x equals 9, and x equals 16, which are my x values. Okay, so we use that point. Okay, if I plug in 9 into this function, the square root of 9 would be 3. If I plug a 16 into that function, square root of 16 would be 4. Okay. I want to draw the secant line. So now to find the average rate of change, all I want to do is find the slope of that secant line. I'm going to label the points to make it really clear. This is 16, 4, and this one is 9, 3. So I'm going to find the slope of the line through those 2 points. So the average rate of change would be 4 minus 3 over 16 minus 9. So that's 1 over 7. Okay, again, that's an increasing function. So my slope is positive, or my average rate of change is positive. All right, so let's come up with a definition of the average rate of change over a certain interval. So we're going to do this in general. So here's just some random function. We don't have an equation for it. It's just an arbitrary any function. We want to know the average rate of change from x1 to x2. Okay, so let's put in x1 and let's put in x2. All right, so if this is x1 and this is my function, then this value would just be f of x1. This is x2. The value of the function at that point would be f of x2. So now we will draw the secant line through those 2 points. And the average rate of change from x1 to x2 is just the slope of the line through those 2 points. So I'm going to label the points. This one is x2, f of x2. This one is x1, f of x1. Okay, so the slope then would just be f of x2 minus f of x1 over x2 minus x1. Okay, so that's the general definition of the average rate of change of a function. And as you can see, it looks extremely like, just because it is the same thing as the definition of slope of a line. All right, let's do another example. So I've given you another function up here, a little more complicated than the others. We're not going to draw a graph of this one. We want to find the average rate of change of that function from x equals 2 to x equals 5. So all we have to do is use the definition that we just had. So let's find f of 2. Excuse me, let's do it the other way. So we want to do f of 5 minus f of 2 over 5 minus 2. Let's work that out. So let's find f of 5. So to find f of 5, I'll plug 5 into the function. That's 25 minus 15, that's 10, plus 1 is 11, minus, let's find f of 2. So I'll plug in 2. That's 4 minus 6. It's negative 2 plus 1 is negative 1, and we'll be really careful to have a minus negative 1. And there's always a chance of making arithmetic mistakes, so let's go back and check, make sure I did that right. It would be really embarrassing if I mess something up here on this video. So plug in 5, that's 25. 3 times 5 is 15. 25 minus 15 is 10. Plus 1 is 11. Plug in a 2, that's 4. Minus 6 is negative 2. plus 1 is negative 1. All right, and then I got 5 minus 2 on the bottom. 11 plus 1 is 12. 5 minus 2 is 3. And I get 4. So the average rate of change of that function from 2 to 5 would be 4. All right, so let's look at an application problem. Okay, so let's say we got this particle, and we got an equation that tells us its velocity, the velocity of this particle at any time t. So here's our equation. I'm giving you a graph of that function. So you can see here the velocity changes. Our velocity is not constant. In the earlier problems we looked at, we had a constant velocity, which gave us a straight line. Here, we've got a curve. Our velocity is not constant at all. It changes depending on the time. Okay, so we want to find the average velocity over a certain interval. Okay, so we want to find the average velocity from time 2 to time 7. Okay, so we do that just like we've been doing. Our time is on this axis, so here's time 2. Here's 7 seconds. We'll draw a secant line. Through those points. All right, let's label our graph. If this is 7, then this would be, put the 7 in, 7 plus 1 is 8, 24 divided by 8 is 3. Put the 2 in to find this one. 2 plus 1 is 3, 24 divided by 3 would be 8. And I'm going to actually label the points. This is 7, 3. This one is 2, 8. All right, so we want to find the average acceleration over that interval. So remember the definition of acceleration is the change in velocity over the change in time. So we have velocity on this axis, time on this axis. So all I want to do is find the slope of that line, the change in velocity divided by the change in time. So we want the slope of that line, change in y, we're changing x. All right, so the change in velocity would be v of 7 minus v of 2. And the change in time would be 7 minus 2. The velocity, or the vertical axis, is measured in meters per second. The denominator here would be measured in seconds because that's our time. V of 7, we already know what that is. That's 3. V of 2 is 8. 7 minus 2. This is meters per second. This is seconds. 3 minus 8 is negative 5. 7 minus 2 is 5. And I've got meters per second over seconds. And so I end up with negative 1 meters per second. And we can write that as meters per second squared. Meters per second would give us meters per second squared. Okay, so my answer is negative, and it should be because that's a decreasing function. So what this means is that for every second, my velocity is decreasing 1 meter per second on average over that interval. All right, so I've given you here a really complicated looking function. We're not going to graph this one. So we're going to talk about some some more strange or complicated elements that we can plug into this function. So let's start off with an easy example. Let's do f of smiley face. Okay, so f of smiley. Okay, so if I say f of something, we take whatever that something is and plug it into the function. So this would be 1 over smiley minus smiley to the 5th plus the square root of smiley minus 3 raised to the smiley power. Okay, so that was simple enough. Now let's try this, f of a plus b. Okay. If I say f of something, you take that something and plug it into the function exactly where the x goes. So f of a plus b, I'll take a plus b, substitute it in for x. So I'll have 1 over a plus b minus a plus b to the 5th power. Make sure the a plus b is in parentheses because I have to raise whatever x is to the 5th power. If x is equal to a plus b, I have to raise all of a plus b to the 5th power plus the square root of a plus b minus 3 raised to the a plus b power. And we'll put that in parentheses just to make it really clear. Let's do one more. Let's do f of x minus h. So if I do f of x minus h, I have to plug x minus h into the function, put it exactly where the x goes up here. So I'm going to substitute x plus h everywhere where I see an x. So that'll be 1 over x minus h minus, in parentheses, x minus h to the 5th plus the square root of x minus h minus 3 raised to the x minus h. We'll be using this a lot where we substitute in things that look very similar to this in just a minute. Okay, here's an arbitrary function. There's no equation for it, we're just making up some arbitrary function. Let's say that we have x here. But if this is x, then this would be f of x. Okay, now we're going to take some tiny little number, maybe a 0.1 or a 0.01, some tiny number, let's call it h. We don't really care what its exact value is, it's usually a really small number, but we're going to call it h. So if I start here at x, and I add that little bitty number to x, h. So if I add h to my x, then this would be x plus h. So say the x was 5 and the h, a tiny little number, let's say the h was 0.1. So if x was 5 and h was 0.1, this would be 5, this would be 5.1. So x plus h here. If this is x plus h, then this would be f of whatever this is. So f of x plus h. Okay. Now, as you can guess, we're going to find the slope of the secant line through those 2 points. So here's my secant line. So the average rate of change from x to x plus h is f of x plus h minus f of x, subtract these two, minus or over x plus h minus x. Right, let's be really clear where we got. So this point would be x, f of x. This point would be x plus h, f of x plus h. So subtract my y's, f of x plus h minus f of x on the top, x plus h minus x on the bottom. We can simplify this. Here I've got x plus h minus x. X minus x cancels out and just leaves me with h on the bottom. So I've got f of x plus h minus f of x all over h. This is a really special equation. We use this a whole lot. I mean, it's the foundation, really, of half of calculus. And it has a name. It's so special. This is called a difference quotient. So this guy is called the difference quotient of f. Okay, let's work with the difference quotient some. Okay, so I want to simplify the difference quotient of f of x equals x squared. Okay, so the difference quotient is f of x plus h minus f of x all over h. Okay, for this example, we're using the function x squared. Okay, so f of x plus h, I should plug x plus h into the function. So I'll put it exactly where the x goes. So that would be x plus h squared minus f of x. F of x is just x squared. And that's all over h. Okay. Now it says to simplify this, so we're going to work it out. We're going to expand this and manipulate it some, see if we can simplify it. All right, so x plus h squared. Hey, don't make this mistake. X plus h squared is not x squared plus h squared. Remember that in order to square something, you have to multiply it by itself. So we have to do x plus h times itself in order to square it. And then we'll have minus x squared all over h. Okay. Remember, to multiply these, we have to use the distributive property. So we multiply here, 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 here. X times x is x squared. X times h is xh plus another xh, so plus 2xh. And then h times h is h squared. We still got minus x squared all over h. Notice that the x squared minus x squared cancel out. So we're left with 2xh plus h squared all over h. I have an h in both of these terms, so I can factor an h out. That leaves me with 2x plus h over h. Check myself. If I distribute this h back, I get 2xh, and I get h squared. As long as h is not equal to 0, we can cancel those guys out. and we're left with 2x plus h, assuming h is not equal to 0. Okay. Okay, let's try another example with the difference quotient. So this time our function is 1 over x. So the difference quotient is f of x plus h minus f of x all over h. For this function, f of x plus h would be 1 over x plus h minus f of x, which is just 1 over x. And that's all over h. Okay, how to simplify this mess now? Okay, so on the top up here you have fractions or rational expressions. In order to add or subtract fractions, you need a common denominator. So let's multiply this fraction by x over x. And let's multiply this fraction by x plus h over x plus h. So now I've got a common denominator. So on the top, I'll have x minus x plus h. Be really careful to leave the x plus h inside parentheses. And that's over x times x plus h. So common denominator, it stays the same. And I just subtract the top, x minus x plus h. And that's all over h. I'll keep all this stuff together. Okay, dividing by h is the same thing as multiplying by 1 over h. So we'll do that in just a second. Up here on the top, I've got x minus x plus h. Now, x plus h is in parentheses, so I have to subtract that whole thing. So it'll be minus x and minus h. So if I simplify the top, my x's will cancel out, and I'll be left with negative h. Here, I'll just leave that like it is. And as I said a second ago, dividing by h is the same thing as multiplying by 1 over h. So times 1 over h. So I simplified on the top. Remember that to include my parentheses, and that's minus has to apply to both of those. So minus x and minus h, the x's cancel, just leave me with negative h. This stays the same. Dividing by h is the same thing as multiplying by 1 over h. Okay. So our h's cancel out as long as h is not equal to 0. So I will be left with negative 1 over x times x plus h, assuming h is not equal to 0. Okay, let me elaborate a little bit on this part about assuming that h is not equal to 0. Okay, so suppose that we plugged 0 in for h here in this equation. If we put a 0 in for h, we would have a 0 on the bottom of a fraction, which is bad. That would be undefined. It would be undefined here. If we plug 0 in for h, we would have a 0 at the bottom, and it would be undefined here. In this last equation, however, if I put a 0 in for h here, I end up with x squared on the bottom, which is okay, assuming that x is not 0. But here, it's okay to have 0 for h. Here, it's not okay. So if h were 0, this expression and this expression would not be the same. They wouldn't be equivalent. But as long as h is not 0, these two expressions are equivalent. So we technically need to make this assumption every time we cancel that h off the bottom. All right, let's do another example of a difference quotient. Let's simplify the difference quotient of this function. Okay, so again, the difference quotient is f of x plus h minus f of x all over h. Okay, for this example, f of x plus h, I will plug x plus h into this function everywhere where I see an x. So that'll be x plus h squared minus 3 times x plus h plus 1. Okay? So all of this is just f of x plus h. So I'm going to kind of put brackets around it to keep it by itself together. Okay, so this whole thing is f of x plus h minus f of x. F of x is this whole expression. So x squared minus 3x plus 1. So this is f of x plus h minus f of x, and it's all over h. That's a mess, but it's not too difficult to simplify. Okay. X plus h squared, we did that just a few minutes ago, so let's take care of it really quickly. That's x squared plus 2xh plus h squared minus, distribute my negative 3, so minus 3x minus 3h plus 1. Okay. And we got to be really careful. We got to subtract all of f of x, the whole thing. So it's very important that you keep all this in parentheses. This minus has to apply to every term inside of there. So minus x squared minus negative 3x would be plus 3x minus 1. All over h. Now we really made a mess, didn't we? But magic stuff happens now. I have x squared minus x squared. Those cancel. I have negative 3x plus 3x. Those cancel. I've got 1 minus 1. Those cancel. See if we can figure out what we've got left. I've got 2xh plus h squared. 2xh plus h squared minus 3h. And that looks like it. Make sure, minus 3h. And that's still all over h. Notice in the numerator, I have an h in each term, so I'm going to factor out an h. That leaves me with 2x plus h minus 3 and an h on the bottom. Just like before, my h's will cancel, assuming that h is not 0. And I'll be left with 2x plus h minus 3, assuming h is not equal to 0. All right, it's time for you guys to practice a little. Okay, so here's a problem. T seconds after an experiment begins, we have a particle that's moving away from a measuring device. This function tells you how far away the particle is, where the particle's at any time t. Okay. I want you to graph that function, and then I want you to find the average velocity of the particle over this time interval. And when you do that, I want you to represent this concept on your graph. So pause the video, work it out, give your best effort, and then we will go over and have a look at it. All right. So first of all, we know what this graph looks like. We graphed it a few days ago. So it's going to go up like this. And on this side, it comes down this way, but we're really not concerned about that in this problem because that would be before the experiment began. So we're just going to look at this part. All right, we want to go from 2 to 5. If I plug 2 into this function, I'll get 8. If I plug 5 into that function, I'll get 125. To find the average velocity, velocity is change in position over change in time. So if this axis gives me the position and this axis gives me the time, change in position over the change in time would just be the slope of this secant line. And I'm going to label these points. This is 5, 125. This is 2, 8. So the average velocity would be the change in position over the change in time. So that'll be P of 5 minus P of 2 over 5 minus 2. And my position in this problem is measured in meters. My time is measured in seconds. P of 5 is 125. P of 2 is 8. That's 2. That's meters. That's seconds. 125 minus 8 is 117. 5 minus 2 is 3 meters per second. And 3 will go into 117 39 times. So we can reduce that. We get 39 meters per second. Okay, so the average velocity over that interval is 39 meters per second. Keep in mind, it wasn't always 39 meters per second. Down here, the velocity would have been lower than 39 meters per second. Up here, the velocity would have been higher than 39 meters per second. But on average, it was 39 meters per second during that interval. All right, second practice problem for you. I want you to simplify the difference quotient of this function. Don't be scared of the pi. It won't hurt you. All right, pause the video, work it out, and then we'll go over the solution. All right, let's have a look. So the difference quotient is f of x plus h minus f of x all over h. Okay, for this problem, f of x plus h, I will plug x plus h in for x. So 3 times x plus h squared minus, very important to have these parentheses. You must have those parentheses around that because you have to subtract the whole entire thing. Plus pi. And we keep all that together. That's all f of x plus h. Now I'm going to do minus f of x minus f of x is 3x squared minus x plus pi. And that's all over h. Okay. So now it's just algebraic manipulation at this point. X plus h we've done already a couple of times. We know what that is. So we would have to work all that out and then multiply by 3. So we know that when we do x plus h squared, we'll get x squared plus 2xh plus h squared. Then multiply to 3. So let's see if we can do that in our head. That should be 3x squared plus 6xh plus 3h squared. Okay. Minus x minus h. Remember that minus sign has to go with both of those. Plus pi. This minus sign has to go to each term here. So minus 3x squared plus x minus pi all over h. And now the miracles will happen. 3x squared minus 3x squareds cancel. I've got minus x plus x, those cancel. I got pi minus pi, those cancel. Right. That will leave me with 6xh plus 3h squared minus h all over h. All right, there's an h in every term on the bottom or on the top, so we're going to factor an h out. That leaves me with 6x plus 3h minus 1. Right? Double check, that's 6xh, 3h squared minus h. And that is all over h. So now, as long as h is not 0, we can cancel them out. And our final answer will be 6x plus 3h minus 1, assuming h is not equal to 0. All right, so if you got all that correct, congratulations and good job. That concludes this lesson.